class. My name is RJ, and this is Design for Dynamic Wearables, a course where we take a look at computational design techniques through the lens of body architecture, fashion, and accessory design. Today I wanted to take a look at the plugin Dendro, as it's a really helpful volumetric modeling tool built for Grasshopper. This is the page for it on Food for Rhino, so we can download it there. Hopefully most of you have it. I would recommend downloading it because it's really helpful going from things like curves or points to more solid objects and meshes that you can easily 3D print. It makes for watertight models, and that's one of the reasons that I mainly use it. So we have Dendro up top in the toolbar here with all the tools that it comes with. It's not that many compared to most plugins for Grasshopper, but the tools that it does have are very, very powerful. So I wanted to do a quick overview of everything just to give you guys a quick setup of what everything can do. So on the first side here, we have the types, which I'm not going to look at because they're mostly just containers for everything else that we have in Dendro. Very similarly to the parameters for geometry and primitive that Grasshopper comes with natively, these are very similar in Dendro. So just know those are there. The main tools that we'll look at are going to be everything under convert. Everything from create settings to changing different data types into volumes that Dendro can use. So depending on what we have in our scene, if we have a curve, mesh, brep as well, subds, anything you can convert into a mesh, or points, we can convert those to volumes that Dendro can then read. At the end, we can convert it back to a mesh if we still want to affect it in different ways throughout our script. So whenever we're starting with Dendro, we want to take stock of what we have and then try to figure out where we need to go. So to start right now, I just have a very simple circle here. This circle, as we know, is a curve. It's what it's defined as in Rhino. So since we know that, we know we can maybe start with the curve to volume component. This is going to be the easiest one to convert a curve to volume. There's other ways to do it. To convert it to a volume, we could first pipe this curve, turn that into a mesh, and then convert that mesh to a volume. Or alternatively, we could also convert this circle into a lot of points and then turn those points into a volume. All those options would give us a similar outcome, but the easiest one right now is to start with curve to volume. You'll notice there's some inputs, and these are similar for all the convert tools. We'll have inputs. For the curve and point, we'll have a radius, and then we'll always also have a settings component. So let's bring everything else out here to compare it to. So we have curve to volume, we have mesh to volume, and we also have points to volume. So the inputs for curve and point are the same, and mesh is slightly different. So we can add this curve to the curve input, and that fulfills the first input for this block. The second one is the radius, so the radius that we want to create a thickness around this curve. So let's add a slider here with a range of values. And then we'll also need a settings tool. So the settings component is one of the most widely used components. You'll use it in every single Dendro script that you write. This component is pivotal. This component is necessary for any script, so we'll always need this, so it's important to know what it can do. The first input here is going to be the voxel size. By default, this is 1, but what I usually like to do for the scale of things I work on, I like to do a slider from 0.01 to 1. And it'll be good to explain right now, before we move forward, what voxels actually are, as this will inform how we move this slider. So if you know what pixels are on a screen, those are lots of cubes. Those are lots of, so if you know what pixels are, those are a lot of boxes next to each other that emit light on a screen. Each pixel is next to another pixel, and those can be arranged in a very regular grid setup, which is great. And this is in 2D. Voxels, on the other hand, are going to be in 3D. So we can imagine that we have cubes and you can do many, many cubes in 3D. And with these 3D cubes, we can start to define volume. So if we have, say, a volume that's quite organic, that's a lot of the things that I work on this channel, we can fill this with cubes. And the way we fill it with cubes will approximate this volume. So it won't be a perfect representation, but it'll try to fill in as much of the volume as it can with as many cubes as it sees fit. So again, these cubes are only approximating the volume. And if we want to be more exact with how we approximate the volume, we can do smaller and smaller cubes, and those will be able to fill in many more details of the volume. So you can see when we have bigger cubes, we don't approximate it as well, but since we have a small number of cubes, this algorithm is going to run really fast. Now, if we want a better representation, higher fidelity of the model, we can add many, many more cubes, but this will run much, much slower. So we get a gain in detail, but a loss in speed. So that's good to keep in mind when you're trying to set what you want the voxel size to be. Okay, each one of these is one voxel, and this has a specific voxel size, and this has a specific voxel size that is much smaller than this one. So this one's very tiny. So we can really relate that back to the slider, where if we want really high detail, we can make this voxel size very, very low, close to 0. If we want very big voxel size, we can put this a lot higher, so close to 1. I will note as well, if you put this down to 0, that becomes an impossible voxel size to hit, and you will just crash Grasshopper. So I wouldn't recommend ever going to 0. And in knowing that, whenever I make the slider, personally, I always like to start with the slider up at 1, at the biggest voxel size, so it runs very quickly. We might not see a lot of good fidelity here, but we can hone this in later and figure out what number we actually need without crashing our computer first. So we can plug the voxel size into S, and with that input, I'll explain the rest of the inputs in a minute, but we can plug that into S, and we will start to get the volume showing up in Rhino. So if we make this number smaller, you can see our detail starts to increase, and we have a much better approximation of the radius around this curve than we did at 1. You can see the facets here. So looking at the other inputs here, we have bandwidth, the ISO value, and the adaptivity for this input. So you don't need to know much about exactly what all of these mean, but I will say that by default, this will give you inputs that run quickly, but they won't be the highest fidelity. So whenever I work, this is just a note, I like to put a value of 3 into the bandwidth. So we give it a little bit more radius around the surface, and that'll just preemptively solve a lot of issues that might come up when doing voxelization techniques and working in this volumetric way. It'll make the surface much more uniform, which we enjoy. And then for adaptivity, it starts at 0.1, but I like to put a value of 0 in here. You can see that this will affect the output polygon size. So starting at 0.1, it'll give us larger polygons. So the polygon count will be low at the end, but if we put 0, we'll have a much higher polygon count, but also a much smoother final surface. So these are just nice to have, but they will add a lot of good detail at the end. So now that we have the curve to volume, we've converted this circle into a volume. With this volume, we can do a lot of different things to it. And that's where the filters and the intersect come in. So with the filter, the main ones here are the offset volume and the smooth volume. And we can quickly see what these do. So we can plug the volume into the volume input, and then we have an offset distance that we can define. So again, let's create a slider for this. And we can see that as the slider gets bigger, our volume also expands at a consistent offset around the surface. You also see that we have a mask input here, and that's going to be an optional input for all of the filters, and we'll look at that in a minute. For smooth volume, we can again run this volume along to the volume input, and we've got a couple inputs here. So first one, we have the optional width of smoothing, so we'll come back to these in a minute. We have the type of smoothing. There's 4 different types. We have the iterations, so the number of times we'll do a smoothing operation, and then again the mask as well. So this circle is already pretty smooth, so let's switch to a different kind of geometry, and we'll take a look at maybe a cube and how that'll look. Okay, so let's create a center box, which will give us a cube. We can plug this into a mesh B-rep to convert that. Now let's just preview this off. So with this cube, we can use a mesh to volume on this one. So again, let's take our settings, plug those in, as well as the mesh, and let's go ahead and convert it into a volume. With our smooth volume, let's take that and we can run this mesh to volume into the smooth volume. Right now you see it's smoothed it down a lot from the original. So let's go ahead and start by taking these settings down, and this will again give us a higher fidelity and make it closer to the original sphere. This setting will also affect how the smoothing works. So if you have a much higher voxel number, one iteration of smoothing will do much more damage or create much more change to your original object. Whereas if we have a much smaller voxel setting number, then our delta of change is going to be much smaller as well on one smoothing iteration. So let's look at these iterations. They're done in integer values. So we can make a slider. Let's just do 1 to 25. And we can see what the smoothing is going to do now if we up this number. So the higher we get to the top, the more it starts to approximate a sphere. As we've smoothed everything out uniformly, all of those harsh edges go down to really, really smooth surfaces. So that's going to be the iterations. On top of this, we can look at the type. There's types from 0 to 3. So I'll make a slider from 0 to 3 so we can select between these. By default, it's at 2. So I'll start the slider there. So we have a baseline. At 3, we go to median smoothing, and you can see the effect it makes when we change our iterations. This was 2. We can go down from mean to Laplation, and we get this kind of smoothing effect. And then we can go from Laplation to Gaussian, and we get a much more effective smoothing than the other 3. This is going to smooth much, much quicker and really round off everything a lot. So on top of those, let's look at the width as well. Again, this is optional. It acts as a multiplier. So by default, it starts at 1. So we'll set that there for a baseline. And then we can start moving this number. And you can see this is just multiplying the iterations. So now every time we slide it, it's going to do a lot more smoothing than when it was just at the default of 1. Again, this is a default. I don't use the width much. And again, we also have mask here. So let's take a look at what mask is. So we'll grab that component from Dendro. And you see we have some inputs here. So we have the volume input, the minimum value, the max value, and the mask invert if we want to change which way it's going. So on that, let's make another box in our scene that we can move around, just like this. Let's internalize that B-rep into Grasshopper. And we'll convert this into a mesh again. And then we'll convert that mesh into a volume, making sure we keep this settings value consistent. One thing I should mention is that, if you haven't noticed already, whenever we're working on a big Dendro script, we'll want to make sure everything has the exact same settings. You cannot combine a volume with one voxel size with another different voxel size. There's no way to compare these because of how different they are. So we need to have the same settings for everything. Okay, so now that we have the mesh volume of this cube, we can convert that to the mask. We have the values here. We'll change these in a second, but we can plug the mask over here into the smooth volume. So let's line this up with one of the corners. And we can see how this will start to affect it. Let's just preview these off. Okay, now we have a mask on this top left corner. So if we start changing these smoothing iterations, we can try to make it affect it. So let's start adding inputs here. We'll start with the toggle. So, okay, if we change this to false, we can see that now we're getting no smoothing in the section where that box was. No matter how many times we smooth everything else, the place where the box was is now no longer going to be smooth. So we can use this in combination with other Dendro tools to make more unique shapes. So we don't just have to uniformly smooth everything. We can choose where we want to smooth or where we don't want to smooth. And again, we have these optional min and max values if you want to change how this transition is taking place. But I'll leave that up to you. It's just number values here that you can add to change that smoothing. But we'll keep moving on from here. So now that we know what smoothing does, we can look at volume blend for a second, and we can see how this is working. It's mostly like a tween between one and the other volume, and that's going to work on this parameter here. So let's preview off everything we've done before. You can maybe use this for animations to see how you start and finish. There are a number of other ideas, but that's the most simple thing. So let's start by adding a number slider here from 0 to 1, so we can grab parameter values for this lowercase t. And then as we move from 0 to 1, we can tween between the two volumes here. And we can see, again, we have a mask, and we have some other options here. But basically, that's how volume blend works. I don't use it much, but it's good to know what it does. So we'll come back to smooth volume here. And let's see about this sphere. So this sphere is very, very big. I'm going to take this mask off for the moment so we can just compare these two shapes next to each other. Let's make this box a little bit bigger, just for comparison value. Okay, that'll do. So now we have two volumes. We have the circle that we thickened, and then we have the box that we turned into volume and smoothed out. So let's take a look at all of our intersection options now. First, we have the difference, and these work just like Boolean. If you're Booleaning mesh or breps in Rhino, we have intersection and we have union. So these three, if you know anything about Booleans, will work as you expect, but let's take a look at all of them. First one with difference here. Difference will take whatever is in B and subtract it out of A. So if we have this cube and we want to subtract this sphere type of object out of it, we can combine those together like that. Let's preview off everything, and now we see we have a hole drilled in the center of this box. If we flip these, now we have a sphere with a box cut out of the center. Okay, so volume intersection. That'll take what is inside both of these shapes. So that'll be easier to visualize. So we'll plug both of these in. The organization of A and B is not going to matter here because the inside of both is going to be the same no matter which way you do it. So now you can see if we compare, this is giving us just the volume that is inside both the cube and the sphere object. So that's pretty self-explanatory. And then we'll look at the volume union as well. This only has one input, but that means we can drag as many objects as we want into this one input. So union will put two objects together. So right now we can see these are separate because we can see this outline going through the box. If we were to combine them, let's hold shift and put them both in. Make sure they're on the same list. If they're on different branches, they're not going to combine. So it's always good to flatten here as well if your intention is to combine everything. So now if we look at just this, we can see that the silhouette now for the sphere, instead of going through the box, it now becomes the box. And now we have one shape. So those are the three intersection options. We also have the I/O here. If you want to read and write volumes from your hard drive, if you're transferring volumes between different files or what have you, you can use those, but very rarely I touch those. I mainly use just the convert, filter, and intersect tools for most of the work. So that's the basics of everything you can do with Dendro. And again, let's take a look at how to finish this here so we can actually see the final meshes. And that's the one last tool that I haven't shown yet, which is going to be converting the volume back to a mesh. So again, we see a volume input and a settings. So good to know we have settings there. Let's take our settings component and plug that in. And then we have our volume, so we can plug that into the volume pair. So now, instead of a volume, which we had before, one Dendro volume, we now have one mesh with these vertices and faces. So now we can bake this out into Rhino, into something we can affect in other ways. So let's just do that quick so we can see the topology here. So you can see it's gone, and we have now these smooth intersections with quadrangulated faces going throughout them. And even looking at this, we can start to make out the voxelization in these cubes like I explained earlier. So we can see there's clearly like a grain here. The boxes follow this XY pattern. And as we go around a sphere, you can see how they're pretty normal here. And then they get more combined on the 45 and then back to this more normal layout here. And if you imagine a volume of cubes going through this, splitting it up into tiny sections, that's kind of shown in the mesh here on this final look. Okay, so let's go back into Grasshopper and just see one more thing. Let's look at the edges here as we view this. So we can see these meshes, these edges on the mesh, and if we were to change this adaptivity value back to 0.01, we can see how the topology changes. So it's a much more random and much less detailed in its organization than when we had 0 in the adaptivity. So it's just good to see what the difference is between those two. Let's bake this out. This is the 0.01 version, and this is the 0 version. And the file sizes between these two are going to be much different. This is a much larger file size than this one. But again, if you're going out to 3D print or render, you're going to want to have the highest detail setting that you can, so you don't see these facets either on the print or in the render. And let's also just disconnect both of these for the moment and see what kind of shape we get without the 3 and 0 being plugged in. You can already start to see that there's some errors here along the topology, which is why we preemptively solved this in the beginning. So if we compare this to the other two, you can see because the ISO value is not 3 anymore, we have these little pockets and holes in the mesh, which are not great for topology's sake, and they're not great for 3D printing as well, because we don't have a watertight mesh anymore. So we don't want to see any of this. So it's just good to start with this 3 and 0 input, as I explained at the top. Okay, so on that, we now know how to go from curves and boxes into a really nice mesh. Okay, so let's look at some points now and some other things you can do with Dendro. So let's start to take a look at what we can do with curve from points. So let's look into this. And we can see, okay, let's start with an input curve. We can just start with our circle from earlier. So let's grab that. And you might want to change the radius, so we'll see how this goes. Let's add a slider in here for the radius. And you can see already what this is starting to do as I built it out. Basically all we're doing is dividing the curve into points and then converting those points into a volume. So let's make this circle a little bit bigger, just so we have more points to look at. And what I've done with this setup is auto-calculated what the settings should be based on what we want this radius to be. So if we were to do this without any of the optimization here, just with these two slider values, one for radius, one for settings, you'll see that we get this error. And this error is telling us that the radius must be at least 33% larger than the voxel size. Right now, 1.78 is not 33% larger than 1.5. So we're getting an error where this is not working. If we were to make the radius bigger, we can see the error goes away and it starts to work again once this value gets above 33% larger than the resolution. And this will work at any larger scale, but it will not work lower. We get that error again. So what I've done is auto-calculated this by dividing the radius by 3.4 and using that to create the settings. I have this resolution here just to change how many points we have. The more points, the better. The less points, we can actually start to see each point as it's creating a sphere around it, kind of next to all the other ones. And we don't want that, so we'll keep this resolution a bit higher. So now we can make this radius whatever we want, and the settings are going to auto-calculate the best option for it. Okay, so that's using points to make volumes. So let's look at how to do this with an attractor point. So let's use this circle again. So now we can see that based on the point that I have on the screen, we're changing the radius of the curve based on how close it is to this point. And you can set that up by putting a variable radius value for every single point on this curve. So same as before, we're dividing this curve into a lot of points with the resolution, just as before, dividing it by 3.4 to make the settings. And then we can measure the distance from this input point to all the other points, and we can visualize that quick by creating lines. And we can see that the distance of this line is a certain value, and the distance of this much longer line is a very different value. So if we have all those values, we can figure out what their domain is, and then with this graph mapper, which is also a separate plugin, Rich Graph Mapper, we can use the graph mapper to change the radius values into this nice gradient. And we can even pull these points around and say change how these values are mapped along the surface and get very different options. Maybe put a Bezier curve in here and change it as well. So very quickly, we can get a little more complex with how we're defining the point and radius values here. Again, the settings are the same for every single point. So I've done a little bit more math to calculate what the setting should be. And right now we're calculating the settings for the smallest point. So we have good resolution for the small point and keeping that for every other point So the settings are really good for the small parts, but technically too small for the large parts. You don't need the setting here, but in order for this alt to work, they need to have the same settings. So we have to find that smallest common denominator between the points and make that the setting value for everything. Okay. We'll take one last look here at this other cluster I have. Let's put our circle in here again.
Okay.
And now we can give the curve start and end thickness, making this sort of spiral on this curve. So same as before, except this time we're not actually calculating a distance between an attractor point. We are deconstructing the curve itself and using the values of the curve to inform what the values of the radius should be. And we can do this for any curve. So let's do something a little bit more abstract here. Great. And let's put this curve in. And now we can see maybe what the use case for this would be. Drawing these curves in space that have a variable radius from start to end. So that's an overview of a lot of the things you can do with Dendro, the basics to a couple more advanced things. So hope this was helpful. As always, I'll leave these files up on my Patreon, so go check it out there. We'll have the files and the video, and you can leave comments and ask questions. But if you enjoyed this video today, hopefully you'll enjoy some of the other videos on my channel or on Patreon. There's a lot more content there, so go check that out. And hope to see you in class next time I post a video. Thank you. Bye.